So last time we had an introduction to the combustion that we're studying in this class. We have reactants, and then they write a chemical reaction equation, and you go to products. All right. Now what we want to do is we want to apply the first law of thermodynamics to the combustion process. What is the first law of thermodynamics all about? It's all about the conservation of energy. All right, so somebody said, write the first law of thermodynamics for an open system. So here's my control volume, like this. And maybe I bring in reactants on this side. We take out products on that side. There's my control volume. Can you write a first law of thermodynamics? What would it look like? Well, we'd have the rate of change of energy within that control volume with respect to time is the rate at which it flows in by heat transfer. Let's stay with the sign convention, Q dot in. And then what do we have? We have it's going out, some sort of out of the control volume in shaft work. Let's put it like this, W dot, out of the control volume. And then we have some mass flow rate coming in and bringing with the enthalpy. Let's already neglect changes in potential and changes in kinetic energy. Let's just only deal with the flow enthalpy, right? And then because we suspect that we're going to want to work on a molar basis instead of a mass basis, let's go ahead and write it not in a mass basis. Let's write it on the n dot, and instead of h, we'll put an h bar. And now these are what's coming in. What's coming in? Reactants or products into the control volume? Reactants. So what we're going to do is we're going to say, hey, I need the sum over all of the reactants that are coming in. And then you have a minus sign and you do a sum of the molar flow rates, the molar enthalpies of all of the products going out. Does that look okay? Now, what you're going to do is say, it's been a long time that you did anything that's not steady state in this class. It's almost all steady state. So there's no accumulation or depletion, no transient term, so that's negligible. That's a big zero over there. And this is the way you would write it. So you would write Q dot minus W dot equal to the sum of the products going out and the molar flow rates, the molar enthalpies, and subtract the sum, the reactants, molar flow rates, molar enthalpies. Look good? Let's press forward. This is the equation they would write it. Now, what did they do here? How did they change that equation from this equation? Well, they probably have written an equation that's like this. Let's say 1 in front of the fuel. Let's pick CH4 as my fuel. Hey, what was the name of CH4? Methane, natural gas. And we're going to then take our oxygen and 3.76 N2, and we're going to balance it, but we know that all the carbon go to CO2, all the H2 go to water vapor, and then we're just going to have 100% theoretical air, so some nitrogen left over, 3.76. Or nitrogen goes for the ride. It doesn't react. Okay. Let's balance this out. We put a 1 in front of the CO2 for the carbon balance. We'll put a 2 in front of the H2O to do the hydrogen balance. Then we count up the oxygen in the products. It looks like 1, 2, 3, 4. Hence, I need a 2 there. And I'll finish this with the multiply of 2 there. Is that a balanced reaction equation? And so what it says is that I have, if somebody said I have the molar flow rate of CH4 is equal to, I don't know, pick a number, 9 kilomoles per second coming in. What does that mean about the molar flow rate of oxygen coming in? Can you tell me what is the molar flow rate of oxygen coming in if the molar flow rate of methane coming in is 9 kilomoles per second? How many kilomoles per second of oxygen come in? 18. Excellent. All right, and then you could come over here and you say, what is the molar flow rate of CO2 going out in the products? This is a reactant. This is a reactant. In the products, put a P for the CO2. How many? It would be a 9 kilomoles per second. And then for the water, number of moles of water vapor, going out in the products would be 2 kilomoles per second. And you do the same thing for the nitrogen. Well, what you can do is say, well, I want to take, and that's H2O going out in the products. Okay. If I do this, I say, what is the ratio of the number of moles of oxygen in the reactants to the number of moles of CH4, the fuel, in the reactants coming in? Yeah, so this is just oxygen. I'm just doing a ratio, and then the molar flow rate of CO2 going out in the products divided by the number of moles. I'm just going to put F for fuel, because in this case it's methane in the reactants. And the number of moles of H2O in the products divided by number of moles of fuel in reactants. For this case, the fuel would be methane for this example that I worked out. What this ratio right here is 2, isn't it? What's this ratio right here? 1. What's this ratio 2? You know what? When you look at those simply are the stoichiometric coefficients, aren't they? It's the 1 stoichiometric coefficient in the balanced reaction equation in front of the CO2, the 2, the stoichiometric coefficient in front of the balanced reaction equation for water, and then the 2 for the oxygen. So what they do for this energy first law is they'll divide everything by the molar flow rate of the fuel, the molar flow rate of the fuel, the molar flow rate of the fuel, the molar flow rate of the fuel. And when they do that, this is very similar to what we've done before, where you had W divided by M dot. And instead of having kilowatts per kilogram per second, you have something like units of kilojoules per kilogram. Remember that? We've done a lot of that. Yes, sir. Well, you're saying this is 2 on the CO2?
Yeah, the N dot for H2O above, like above all that, where you have all your N dots labeled out.
All right, I have an error. That's what you're saying. Where is my error again?
H2O. That 2 should be 18.
Oh, right here. Yeah, this is 18. That's right. 2 times 9, 18. Thank you very much. So now this is very familiar when you see this power divided by a flow rate. And so what the units would be is kilojoules, but not per kilogram. Look at the SI units. What would this units be? Kilojoules per kilomole, wouldn't it? So it's very similar to what you have a background with. And then you look at this molar flow rate of each of the products divided by the molar flow rate of fuel, and the molar flow rate of each of the reactants divided by the molar flow rate of the fuel, and you find that those are simply the stoichiometric coefficients. Now don't ask me why. Different books will use different symbols for the stoichiometric coefficients. This textbook uses simply N for each of those stoichiometric coefficients, either the products that are exiting or the reactants that are coming in. I've seen other books, they'll use nu. Maybe nu was a chemical, if you go back to your chemistry class. Oh yeah, that was my symbol for the stoichiometric coefficient, nu. All right? Why don't I really like N instead of, well, because it's so close to N dot. That N there is a stoichiometric coefficient in your balanced reaction equation where you have 1 in front of for the stoichiometric coefficient on the fuel. And so this is the first law, a preferred way of writing it in this textbook. Okay, so let's list out again. If somebody said I'm burning a hydrocarbon, that would be in the reactants. I would need to have each of the reactants. One of them would be the hydrocarbon, one would be the oxygen, and the nitrogen's not a reactant, but that's where it would go because it's coming in with the reactants. And then going out, carbon dioxide, water vapor, and your nitrogen going out. Well, this begs the question, how do I get these H bars? How do I find the enthalpy, the molar enthalpy for things like CH4? How do I get the molar enthalpy of oxygen? How do I get the molar enthalpy of nitrogen? the molar enthalpy of carbon dioxide? Well, they're going to be a function of some things. These behave as ideal gases, very good. Sometimes your water, H2O, can go out in the liquid state, so they'll put like an L there, emphasizing it goes out of liquid state. Or sometimes your fuel comes in, like your not CH4, but your C8H18 could come in the liquid state, octane, or they'll emphasize C8H18 coming in the gaseous state. Professor, we learned F and G stemming from the German words in the beginning of the origins of thermodynamics and the maturation of that subject of study of thermodynamics. Why didn't they stay with the F, for the liquid, and the G obviously for the gas? Well, don't ask me all these questions, okay? They just put L for liquid, so if it's a liquid, it's a liquid, and G for gas, okay? So, when you try to put these all on the same energy scale, it can be challenging. And thankfully, we have a lot of people have worked on this problem before us, and they struggled with this word. What's that word? Datum. That's kind of like the baseline where you're starting energy measurements. And where you're starting the energy measurement has to work for the carbon in the carbon dioxide, the carbon in the hydrocarbon fuel, the water, the hydrogen in the water, the hydrogen in the hydrocarbon fuel. So they really struggle with it. A lot of it is the chemist. Maybe you remember this from a chemistry class. So, datum, that's the fixed starting point for a scale, in this case, energy scale. And the standard temperature and pressure is 25 degrees C and 1 atm. That's kind of like the worldwide average surface temperature pressure. And they pick stable elements at the standard reference state that have a 0 enthalpy, and then the chemist worked hard to figure out what's stable and what's not. And so if you said, is carbon monoxide stable? You'd say, no, it likes to combust. But then they have to break it down into the smallest elements. So what we do is we benefit from the contribution of a lot of other people that have gone before us who've worked this all out. And now we go to this table A25. And we're introduced not only to different substances, the formulas for the substances, the molar masses, some of that's new, some of it's repeated in other tables, but this is the key information right here. It's the enthalpy of formation, H bar, standard temperature and pressure at standard conditions. The subscript F is for formation, enthalpy of formation. It's on a molar basis. Let's take a look at the units. It's kilojoules per kilomole. All right? Now, they picked the hydrogen, the diatomic nitrogen, or N2. They picked the diatomic oxygen, O2, to have 0. This must be where it's like the datum point, the beginning. And then the carbon monoxide is not 0. And neither is the carbon dioxide, water vapor. This is the water is a vapor state, the water in a liquid state. Here's methane. They don't have methane in liquid state. It would be really super cold. So it's just gaseous. Here, though, they have octane, which the gasoline, that's an indication of gasoline, C8H18, gaseous or in a liquid state at those temperature and pressure conditions. So you have different values for the enthalpy of formation. So if you're interested in calculating that enthalpy, here, H bar, for each component, it would be, give me the enthalpy of formation so that everybody starts at the same datum point, and the deviation of that molar or molecule's enthalpy from the datum point. So this would be for each of those species exiting as well as entering. What's the new idea? The enthalpy of formation. Okay, what this one is typically broken out to be the enthalpy molar basis at the temperature that it's exiting minus the molar enthalpy at the reference, 298 Kelvin. Isn't that 298 Kelvin? 25 degrees C? And a lot of them behave as ideal gases, hence they're only a function of temperature. So this delta H bar is calculated also using a table. So the enthalpy of formation in this table A25, and then what is it, table A23? They have for select ideal gases the enthalpies as a function of temperature, the molar enthalpies. All right, let's jump into a problem. We have methane at 25 C, 1 atm enters a furnace operating at steady state and burns completely with 100% theoretical air. Entering in a separate stream. Okay, the air enters at 350 Kelvin, 1 atm. The products of the combustion gases exit at 590 Kelvin, 1 atm. Kinetic potential energy effects are negligible. Okay, so make a sketch. You have methane, CH4. It's at 25 degrees C, 1 atm. Might as well put 298 Kelvin right there. Okay. Then we have air, and it comes in not at 298 Kelvin, but 350 Kelvin, a little warmer in 1 atm. And then out of the combustion chamber, the products all exit at 590 Kelvin. It's still 1 atm. Okay. Kinetic potential energy effects are negligible. I'm so glad that's true. Simplifies it. Determine the energy, the balanced reaction equation for this combustion problem. Well, we just did that, didn't we? This is almost going to be the first step in solving all your problems in chapter 13. Get a balanced reaction equation. So it's methane with 100% theoretical air. So this is it. So we have the 2 in front of the O2 so that we get the 2 and the 4 on the oxygen. Carbon balance, hydrogen balance, oxygen balance. Now, why do I rewrite it like this? Once you start in with the energy equation, it's going to be better to just have coefficients in front of each of them by themselves. So go ahead and multiply that 2 times the 3.76 and get the 7.52. It'll make your life a little easier. So this is the equation right here that are looking for, that you should be able to get, right? That's going to be the starting point. Before you can do an energy balance, you need that. All right. Once you do that, let's continue on now. You have that equation in front of you. It says, determine the heat transfer to the furnace from the surroundings. So this is the control volume where you're bringing in your fuel, you're bringing in your air and fuel, and you're going out with products. And that's a furnace. And look at the wording, to the furnace from the surroundings. This is the direction they're saying for this Q dot. Now we continue to read. In units of kilojoules per kilomole of fuel. We're not asked for Q dot, we're asked for Q dot divided by N dot of the fuel being methane. Now the units work. The units of this, aren't they kilojoules per kilomole of methane? Yeah. So that's the units. So I know the first time you're introduced to problems, you struggle with the wording. Exactly what am I asked to solve for? All right, so now if I think about it, what's happening inside this furnace? Combustion. Your experience. Combustion makes things hot. It's a heat release. It's exothermic. From chemistry, you had exothermic reactions, you had endothermic. Endothermic are rare, but they actually, in a chemical reaction, would make things cold, the products cold. Anybody have those ice packs and stuff or gels, and they break them and they undergo some chemical reaction and it gets cold? It's rare, but it does happen. Most times you have combustion or something, reactions, it's exothermic. Okay, so we would anticipate this answer to be NEG, negative. Now if we look at, this is our answer, what is in front of that a negative sign. So right away, this is tricky in this chapter. A lot of our answers are going to be negative, right? So because it's combustion and the way they word it, it'll be a negative heat transfer. And look at the units. Okay, you already have the reaction equation. How do I get the first law? How do I get that energy equation again? Well, we did that, right? We had the Q dot divided by N dot of the fuel. Hey, that's what I'm looking for. Minus W dot divided by N dot of the fuel. Almost always, there's no shaft work in or out. Almost always. But I don't know why they leave that term in this equation. Maybe it's so you feel warm and fuzzy, like, oh, I recognize the pattern here. When I see a Q dot, next should follow a W dot. Great. But almost every time it's struck out, it's zero. Because there's no shaft in or out of that furnace. Okay, and then what do we have here? We have equal to the sum over all the outgoing products, the stoichiometric coefficient, and then that molar enthalpy. That molar enthalpy we replace by an enthalpy of formation at standard conditions. That's what that zero up there means, standard conditions. Hey, what was our standard temperature? 25 C, 298. What was our standard pressure? 1 atm. Exactly, that's what that means. What's this bar over top? Remind me, what's that bar mean again? On a molar basis. What's the subscript F? The enthalpy saturated liquid. Man, you learned it too well in Thermo 1. Now you have to unlearn what that subscript F means on an H. For this, it means the formation, standard enthalpy of formation. All right, let's continue on. And then we had the, let me write it out. A lot of times they'll put a delta H bar, but think of it this way is the H bar at the temperature of the products minus the H bar at 298. Well, Professor, you put a number in there, 298, and yet the other times it's symbols. Okay, great. Introduce another symbol and call that T naught? I don't know, but the book doesn't. That's our standard reference temperature, 25 C, 298, because it was a delta H, right? Okay, let's continue to write out our equation. So then we do a sum over all the reactants. What is that N? Is that a molar flow rate, or is that a stoichiometric coefficient in our balanced reaction equation? Stoichiometric coefficient. The book probably could have used nu or some other thing used in chemistry for stoichiometric coefficients, but they didn't. So let's press on. We have H naught bar F plus the enthalpy at the temperature that the reactants are coming in. Now I got to get rid of this red stuff here. Put a bar over, right? And then minus the H bar of the 298 or the reference temperature. Now, this is summed over all the products. The products exit. I'm trying to follow the notation of the textbook. They put E for exit on the subscript. And then reactants, they put I. I can never figure out what the I is for of the reactants. Inlet. Yeah, that must be what it is. Go ahead and bust it out. So let's do this. I have my reaction equation. How many products do I have? 1, 2, 3. I need 3 things. So let me go ahead and write it. I'll have a stoichiometric coefficient for the CO2. I'll have the enthalpy of formation of the CO2. I'll have the molar enthalpy of the CO2 at the product temperature. Did they tell me the temperature goes out at 590 Kelvin? Minus the CO2 enthalpy at the 298 coming in. Professor, this is looking super tedious. Yes, it is. It's super tedious. You have the stoichiometric coefficient for the H2O. You have the enthalpy of formation of the H2O. You have the enthalpy of the H2O at the 590 Kelvin. You have the enthalpy on a molar basis of the H2O at 298 Kelvin. Professor, you have absolutely convinced me. This is super tedious. The stoichiometric coefficient of the N2, the enthalpy of formation of the N2, the enthalpy of the N2 at 590 Kelvin minus the molar enthalpy of the N2 at 298 Kelvin. Finally, I now can start the sum of the reactants. How many reactants do I have? 1, 2, 3 reactants. I'll take a negative on the stoichiometric coefficient of the CH4. The enthalpy of formation, I put a not up there, of the CH4. Now, I can abbreviate this a little bit. They don't tell me anything other than the fuel is at 25 C. If the fuel is at 25 C, there's no difference between, so that's it, I end it right there, right? Otherwise, okay, you want me to write it out? Okay. The enthalpy of the CH4 on a molar basis at the temperature at which it's coming in, 298, minus the enthalpy of the CH4 at the temperature reference, 298. Look it, that's why they cancel. All right? All right, let's continue on. Minus the stoichiometric coefficient on front of the oxygen, the enthalpy of formation of the oxygen plus the molar enthalpy of the oxygen. What temperature does it come in at? 350 Kelvin minus the enthalpy of the oxygen at the reference 298. That's why a lot of times we like to bring fuel in and all the air in at the standard condition. Otherwise we have this, okay, it has a temperature at which it's coming in, different than 298, temperature at which it's going out, different than 298, etc. One other term I need to scoot down, negative number of moles, the stoichiometric coefficients of nitrogen, enthalpy of formation of the nitrogen plus the molar enthalpy of the nitrogen at 350, because that's the inlet temperature, minus enthalpy of formation of the nitrogen at 298. It is strongly recommended that you write it out like this by hand a few times in your life, so you don't forget some terms. And then you begin the hunt, because you have to go back to that table, is right here. And then you kind of remember things, don't you? And you say, oh, well, we have oxygen coming in. Oxygen comes in as gas. Hey, what's the enthalpy of formation of the oxygen? 0. Hey, while we're there, let's take a look at the nitrogen gas. What's its enthalpy of formation? 0. So I can jump to my energy balance equation, and I have to scroll down, sorry. For the nitrogen, enthalpy of formation, I forgot my not, standard condition. So those are oxygen and nitrogen. There's my nitrogen, it's 0. I have to get the enthalpy of formation for the carbon dioxide, water, and the methane. Come back to my table. Here is my, where's methane? Methane right here. This number I need, negative 74,850 kilojoules per kilomole, right? That goes in. That's my standard enthalpy of formation. Okay. What about the carbon dioxide? I need this number, negative 393,500. Okay. The other one was the water, H2O. I have a choice. I have to look in the table. Does it go out as water vapor or water liquid condensate? It's a little bit of a, call. You have to say, what temperature was it? 590. Is that a little warm? Yeah, it's a little warm. So it's going to go out, and I pick the gaseous. And probably the wording and said it's gaseous water vapor exiting in the problem statement. Good. We're going to get to condensing furnaces. Who's ever heard of a condensing furnace? Okay, you all have lived too long in Texas. If you are up north, anybody ever lived in Minnesota, North Dakota, a place like that? Condensing furnace. You think about it for a minute. This is like an oxymoron, right? Jumbo shrimp as a food, that's a classic one. Jumbo shrimp, that doesn't make any sense. Okay, condensing furnace, it doesn't make any sense. But guess what they try and do to get the last bout of heat out of that propane or out of that methane, the natural gas, when they're burning it in the middle of winter to keep your house warm? They want very little hot gases go up the flue. and out exiting the house. And they would like to get the heat out, and so they want the water to actually condense. Condensing furnace, look it up on your phone. All right, we'll get into that maybe this time, the next lecture. All right, so let's go in here. So we get this one, and we get this one, and we get those out of the table. Now we go to another table to get what is the CO2 at 590, subtract it from the CO2 molar enthalpy at 298, likewise water vapor and nitrogen and CO2 again, or no, that's O2, and then nitrogen again. So I think I have a copy of the table, maybe I don't. Okay, I don't have a copy of the table, but these are all numbers worked out. So this will be for the reactants, nitrogen and the reactants. This will be at 298. This will be at that, what did it come in at? 350. And then here is nitrogen in the products. Here's the same molar enthalpy at 298. But this molar enthalpy is not at 350, the inlet temperature. It's at 590, the exit temperature. Not only are the equations long, but you have to go and get a lot of numbers out of tables. Okay? But once you do that, you lay it out, you do the math, you get the final answer. It's a negative because it's exothermic. It's a negative 720,933 kilojoules per kilomole. Why do you have 6 significant digits? I'm just keeping all the digits, okay? All right, if I was going to box it as my final answer, I'd round it off to 3 or 4. Oh, here's the table. So here is the 298 is a line in the table, right? Right here, 298. And then for this problem, you had to go and get a value, what, at that, or did you have to interpolate even? Yeah, or 590?
Yeah, it just comes out, it goes out at 590.
590, okay. So I was just going to show you need to get the molar enthalpy of the carbon dioxide, boom, and boom. And also the water vapor, and molar enthalpy. Nitrogen, the nitrogen goes out in the products, right there and there. Can you do this on the exam? Good. So as a summary, here is our energy equation. Looks familiar. Sum over the products, then sum over the reactants. You can also rewrite this by grouping all the enthalpy of formations together. And when you do that, you can introduce a new term called the standard enthalpy of combustion. This does not take into account the temperature of the products or the temperature of the reactants. This is just the enthalpy of formations and the stoichiometric coefficients. Now, you can then rewrite this one as one number, the standard enthalpy of combustion, and then the deviation for each of the products from the standard 298, as well as the reactants from the standard 298. All right. So this number could be tabulated for a particular fuel. Let's say CH4, methane, C3H8. Hey, what was the name of C3H8? How about C8H18? Octane, methane, propane. Propane in the middle, right? Very good. I'm sorry? That's good. All right. Calculate the standard enthalpy of combustion. Hey, is that the H, R to P? I wonder why they picked R to P. Well, going from reactants to products, so it's subscript RP. On a molar basis. All right, so the standard enthalpy of combustion. Is it this term right here that we're asked to calculate? Yeah, that's how we calculate it. So we come over and we say we need to take the sum of the stoichiometric coefficients, the enthalpy of formation for each of those products, the sum over all the products, and then subtract the sum, the stoichiometric coefficient, enthalpy of formation all of the reactants in our equation. Now, when they say that it's for the combustion of methane, it's like CH4, and then you're going to have your O2, and it's going to go to CO2 and H2O. Let's do a quick balance on this. This is going to be a 1, this is going to be a 2, and this is going to be a 2. Right? Now, if you want, you put the 3.76 N2. All right. Now, let's go over here, and I'll just finish this out. This is 7.52 N2. All right. So if I make this calculation for each of the products, okay, I'm going to have the stoichiometric coefficient of the CO2, and then I'm going to have the enthalpy of formation of the CO2 plus the stoichiometric coefficient H2O, enthalpy of formation H2O, and then stoichiometric coefficient of the nitrogen, enthalpy of formation of the nitrogen minus. Then we bring this down here, we have the stoichiometric coefficient of the CH4, enthalpy of formation of CH4, plus the stoichiometric coefficient oxygen, enthalpy of formation oxygen, and the stoichiometric coefficient of the nitrogen, enthalpy of formation nitrogen. Okay, that's what I'm asked to calculate. I pause. Do I have any errors in my equation? Oh, let me do this. Put minus that. A minus and a minus there, right? Stoichiometric coefficient nitrogen. Okay, I think it's okay. This is, it's a wraparound equation. And each of those terms are minus, minus, minus. All right. Which terms have a 0 value of enthalpy of formation? The nitrogen, you're absolutely right, and the oxygen. So the nitrogen. So right away, the enthalpy of formation really doesn't matter where you get the air or the oxygen from. You could get it from pure oxygen or from air, because the enthalpies of formation of the oxygen O2 and N2 are 0. Okay. This one you look up in our table. We looked it up before. Carbon dioxide, you look up in the table. This is, I think I crossed out the wrong one, isn't it? No, that's the nitrogen. This is H2O. I left off a H2O, water vapor, right? And so this is 0 here. You have to look up that enthalpy of formation H2O. You have a choice there. Is it going to come out liquid or is it going to come out gaseous? Most people would say it goes out gaseous. Is gaseous at a higher energy state than the liquid? Yeah. Yeah, it is. Okay. And then for the coefficients, this one was 1. This one was 2. And this one is 1 again, right here. 1. 1. When you do the math, you calculate that it's negative 802,310. So if the products went out at 298 and the reactants came in at 298, that's the heat release that would go out in the form of heat transfer. Negative, because it's really an out, 802,310 kilojoules per kilomole. Here it is in more detail, but there's the bottom line. All right, when computing the standard enthalpy of combustion, it matters if the fuel is liquid or gaseous. Clicker question. Does it matter if the fuel is liquid or gaseous? All right, we back up a little bit because we just did it for this fuel, which was methane. Now, when we think of methane, we go back to our table. Where is that table? Table. Do we have methane liquid, methane gaseous? No, they just say CH4 with a parenthesis G. It's just gaseous. at the standard conditions. But we talked about octane. You could have, last time I filled up my car, I poured a liquid octane or liquid gasoline in my car. Now it'll evaporate, I know, but it's gaseous and liquid. It could be liquid or gaseous at that condition. And you get a different enthalpy of formation depending on the condition of the fuel. So for methane, it really doesn't make any sense. But for others, like C8H18, it does make a difference. So let's go ahead and just grade this. It matters if the fuel is liquid or gaseous. It sure does. The standard enthalpy of combustion. Hey, is that what this term is? Yeah. For a fuel is higher when it's combusted using pure oxygen than when using only air. So we'll stop it. And we'll go ahead and show the results. It really does not matter how the oxygen gets there, if it's coming from a pure source or from air. Okay. I have more of these to play with. Do you want to continue? Yes. You like them? Yes. All right. So let's do A, B, or C. Which one do you want to look at? A. B. B is shorter, less words. All right. When computing the standard enthalpy of combustion, it matters if the product, water, H2O, is liquid or is gaseous. And let's show this. It does matter. It does matter if it's liquid or gaseous. So now let's go back and revisit this table A25. Again, we were introduced a list of substances, the formula. Notice that sometimes they put a little parenthesis S. I still have not figured out what that parenthesis S is. Solid. Hey, that must be it. Just like in parenthesis G, and then the parenthesis L, somewhere in here, there's got to be a liquid. Okay, the molar masses, it's good to have them in the table. The enthalpy of formation, notice the units, notice the symbol. Some of them have 0 values, most of them don't. All right, the Gibbs function of formation, guess what? SKIP. Okay, what about the absolute entropy? You know what? I'm not going to cover the second law for reactions. I'm just dialing back to class, okay? Previous semesters, they got more for their money. Now you're paying more tuition and getting less education. Congratulations. SKIP. All right. But this table I want to cover right here, heating values. A lot of times we burn things like methane to heat something. I mean, really a lot of combustion just to heat something, hence interior of a house or in a furnace in an industrial plant. And so what they'll have is they'll have a heating value. Now they put two values listed over here. One, they put LHV and the other HHV. Both of these are heating values. Why one has an L in front, one has an H in front? One is lower, one is higher. How in the world do they have two heating values, let's say for the methane? Is it that the methane comes in at a liquid state or a gaseous state on the input? No. It's always coming in at the reference temperature and pressure, and it's always gaseous. So what leads to a difference in these heating values? How the water, which is one of the products, goes out of the combustion chamber. This number right here and that number right there, if you have a lower heating value, your product of H2O in the products is going out in the gaseous state. If you have a higher heating value, the H2O in the products is going out in the, not gaseous, liquid state. Now, what did we solve right here? We solved for right here. This problem. This was methane, and the water went out as gaseous. We had this number right here for our standard enthalpy of combustion. I think there's a relationship between that number. Can you write it down on your piece of paper? Because I'm going to have to leave this screen. It's negative 802, 310. Pay attention to the units. Kilojoules per kilomole. Kilomole of what? Oxygen? No. Kilomole of the fuel. How many kilojoules per kilomole of fuel? You got that number? And it's for H2O and the products going out gaseous. There's a relationship between this number, what was the name of it again? Standard enthalpy of combustion. And one of these numbers, the lower or the higher heating value, because the water going out in a gaseous form, there's a relationship between the number you just wrote down and this lower heating value, this number right here, 50020. But what are the units on this heating value? Kilojoules per kilogram. Kilogram of what? Kilogram of the fuel. What was my fuel? Methane. Here is a relationship between kilograms of methane and kilomoles of methane. Can you take the two numbers, combine them in a way to get this third number? Can you use this 16.04? How do you do that? How do you go from the standard enthalpy of combustion to the lower heating value? Divide by the molar mass. And so, let me show that right here. So you use the molar mass of 16.04. You take our standard enthalpy of combustion, you divide it by the molar mass, and you get this number, which is essentially the same number in our table for the lower heating value of the fuel. Okay. If you go back and you compute the standard enthalpy of combustion, assuming the water goes out as liquid, you can then divide by the molar mass and get the higher heating value. All right. Okay, I forgot to emphasize that there's a lot of fuels and you can find their heating values in a lot of places. Okay, how many people purchase gasoline and put it in their car and they're price sensitive? They know that the price of gas is up by about 10 cents last week or whatever. You know, I mean, you buy gasoline, right? Now, what are you buying when you buy a gallon of gasoline? You're buying a heat release. That's what you're buying, right? I know that a gallon gives you a certain amount of pop, of heat release. Okay. Somebody says, I'm buying gasoline which is modeled as octane, and this is it, H2. This is what I like to buy. Okay. I look on the pump. What did they say is 10%? They displaced 10% of my octane by something else. What other fuel did they put in there that's not ethanol? Do we see ethanol anywhere around here? All right, so here's my ethanol. Now, somebody says, I'm going to take and compare the heat release from 100% octane versus 90% octane and 10% ethanol. Okay. You're purchasing heat release as a mechanical engineer. What do I want more of? The more burned, the more. So let's take a look at the ethanol's heating value. Let's take a look at the lower heating value of ethanol and the lower heating value of octane. I know that you've had the blend of 10% in the car so long that but when I taught this class a couple years ago and they were making that transition, students in the class were saying, hey, I've seen a drop in my MPG. I have seen a reduction in my fuel economy because they now are selling me this 10% ethanol. What are they? Look at that. It's a lower heating value. Yep, you're right. You're absolutely right. Now, again, I'm comparing 100% octane, which is aircraft grade fuel, with this. So the heat release for a typical gallon of gas will be a lot closer to the 44,000 number right here than the 26,000. But there you go. Now, How many people have these flex fuel vehicles which can take what? 85? E85. And if you do this, and a lot of people do this for like high school science fair project or something like that, they'll have a flex vehicle. This was a couple years ago, I've seen it. They'll fill it up with gas, do a couple round trips or couple tankfuls of gas, and then really get a good number for their miles per gallon. Then they'll do the flex fuel over to the E85. And guess what they find? The substantial lower MPG with the E85. Surprise. And because you're getting less heat release. Okay? All right. Well, hopefully some of the things in this class are pertinent to your life after you pass this class. Well, we have too many other questions, but here is a summary of today's. So we've covered the first law, enthalpy of formation. What was that? That's this term right here, the standard enthalpy of combustion, and our heating values. I'll see you next time. Thank you very much.